I know. Oh.
So yeah, so Anna Burke wanted to talk about, there's a club for sustainability. I forgot the name already. It's like, but yeah, maybe she can, they're having a meeting tonight. And it's free pizza.
Yeah.
But no beer.
Of Net Impact UC, we're a sustainability organization on campus. We bring in speakers, do speaker panels, we do workshops. We also have a more consulting side of it, but you can learn a little bit more at our kickoff meeting tonight. We'll have pizza. It's right after this class at 5 o'clock. So just come and join in and learn about Net Impact UC. It's at the Couch Attic. It's in Linder. It's at the very top of the building.
All right.
I'll be here, so if anybody wants to follow me over after class, you're more than welcome to. I'll stick around for a couple minutes, but.
It's like you bring in speakers, and what else do you do? Oh, you consult with companies?
Yeah, we have a consulting branch where you'll have to do some training before you can actually do the consulting work with companies. You can do that this semester, and then next semester you'd be all set to work on it with actual companies and even work with the city of Cincinnati. I was like, we have lots.
How many people? How many are in the group?
About 30, 35.
And they're all different kinds of engineers?
I was like, no, we have different types of majors. We have business, marketing, all the way to engineering, criminal justice. I was like, it's really
okay. But you're
open to everybody.
you're a chemical engineer?
Yes, I am.
Okay. I know I've seen your name, but I never saw you actually. You know, like anyway. But yeah, all right. So that sounds good.
That's it.
People want to do that.
There you
Yeah. All right. So I wanted to I sent out, like, I got an email, I get emails from the EPA, but they sent one and it had a bunch of links in it, and they're all like stuff to do with this class kind of. So I thought I'd just forward it along. So sorry for the spam thing I sent out, but if you got it. If you didn't, it's good. But anyway, all the links go to different, there's like at least 6 links in there that go to kind of interesting things that their EPA has going on. I might use some of that for the regulation part of the class later on. And then also I put up, so I have the things for videos for the class should be running, I guess. Oops, it didn't seem to work. I guess I'll have to fix that. Those are supposed to go to a video. Class 1, why didn't it? Did I put it in the wrong place? Nope. All right, I'll have to figure out why. Oh, I know why. This probably hasn't updated the. Hold on a second. Like sometimes it doesn't refresh. No. Anyway, supposedly that link would go to videos of the class from before they're recorded on Zoom. Anyway, so the homework looked good. Like everyone did well in the homework. One of them I didn't grade yet, but all the rest have grades. So that should be okay. That'll probably be like how it'll go like every week, you know, the same. And then the final homework I think is an individual one, right? So all right, so I wanted to basically this section overview of plastics. All right, so this is the map of kind of the total plastics production, and it's mostly polyolefins. So next a week from this Thursday, Brian Brees is going to come in from Lyondale and he'll talk about polyolefins. So, but I'm going to go through a little bit like before that, so you kind of know what's going on. And then actually we'll have a tour of Lyondale at some point pretty soon, you know. And the Rumpke tour for the recycling is October 11th, which is a Friday at 1:30. But all right, but they shut down at noon on Friday, so it won't be operating. But so as a negative, you don't get to see the stuff flying by. But the positive is that you can hear the guy actually, because it's really noisy. Seems like semi-dangerous, you know, because it's an active kind of assembly line thing. So anyway, it should be as a negative and a positive to having it shut down when we go there. So you can still see quite a bit, I think. And then All right, so yeah, that's it. So what I want to do is kind of go through the types of plastic. Again, like the polyolefins are going to be the majors. It's like the low density polyethylene, high density polypropylene, all the kind of yellowish, reddish colors or all that. And then PVC is also more or less a polyolefin. So that would add on to that. So you can see it ends up being, supposedly it's 80% of the plastic waste. I think that's because it isn't here. It's like 50% here because the other polymers, so these are all like high turnover packaging materials, like less than a year probably. And then they're thrown into waste or recycle. And the other polymers are like polyurethane would be like insulation and coatings and things. So it doesn't a lot of it doesn't get to the recycle stream. And then PET is a big chunk too. So in terms of the recycle, 80% is polyolefin. And then this is a production. So anyway, so that's kind of the scheme of things. So what I wanted to do this week is give you like I went through already like the petrochemical sourcing for the kind of the monomers more or less, basically a catalytic operation to make olefins. And then the olefins are then processed to make things like diamines and dialcohols to make condensation polymers like nylon. So basically, olefins are the feedstock to a lot of the different kinds of polymers. So basically, the same picture of crude oil to kerosene and then cracker to make olefins is kind of the picture. So it's a split of the oil production is being cut off to make plastics. So in other words, if we continue to use gasoline, we're going to have these cuts. Also, we can adjust it a little bit, but basically, you're going to have material that'll make monomers for polymers. You have to get rid of those monomers somehow if you're burning gasoline, right? So that's something to think about. Like it isn't necessarily just getting rid of plastic isn't solving the problem totally. I'm going to go to 50 here. Yes. So let's see, 50. So anyway, this is off the top of my head, the 21 plastics, I think it probably is fairly comprehensive. So it's a lot. Basically, I'd like to go through each one and kind of just at least one slide to say like how it's made, how it's processed, how it's used, and then so you have a rough idea like what the picture is. But again, like the main things are going to be like polyethylene and its different manifestations, and then polypropylene and PVC. So like these three are the 80% of what's going on. And also, so PET is the number one that could be recycled. That's like 16%, I think, of the waste stream. And then polystyrene is not recycled. SBR, so the rubbers are recycled as grind for a reuse, for different use, like a lower grade use. Polybutadiene. These are supposedly biodegradable polymers. These things are not recycled. These are water soluble polymers, pluronics, all those three. And then I think most of the other things are not recycled at all, right? But they're also not used as much, right? So these are like electronics polymers, like the thermoset polymers that react, and then it's a permanently cross-linked material, right? So anyways, and then I can, yeah.
This polycarbonate different things.
I didn't put polycarbonate down. I'll have to put that in. I'll mark it down. Yeah, polycarbonate is a condensation polymer too. And it's not recycled, right? So yeah, so that's it fits in. It's not recycled. It's not reused either, because most of the, like if you have a hard plastic like polystyrene, and it's mostly used because it's clear, right? So it makes a nice clear material for Scotch tape container or something. Then if you recycle it, you get something that's like gunky. It's not going to look nice. It's not going to perform as well. And polycarbonate can be used for like windows, like subway car windows and things. So because it's really tough, and CDs. So like a CD, you're not going to use a regrind in the CD. It's like it'll make it kind of useless. It won't work, right? It'll be a mess. So anyway, so So all those that are like that kind of hard, especially like PMMA, so plexiglass, like you can't really recycle because the use of it is to be a clear material, so it's like not going to be clear once you recycle it. If it has some of it will have pigment in it, so it's kind of a total mess. But we don't make that much of those things. Like we're like 80% of what we make is polyolefins, and those can be recycled. And it's possible they aren't being totally recycled, but they could be, so, and also there's also kind of downgrading of it into park benches and lumber and stuff. So lumber seems to be really taken off, actually. Like everyone that's putting in decks now, nobody wants to use wood because it rots. You have to keep, it's expensive, but but anyway, this is another place where you could reduce the price by putting in regulations too. But all right, if you consider like that the thing's gonna rot in 20 years and you don't need to replace it, it's plastic. And you don't have to refinish it every 3 years or something, then it's kind of a better deal. I think in the end, if you calculated it, I think it would work out. That would be an even trade-off at least. So, but anyway, the bottom line is that people are choosing them now, right? Everyone, because all right, the manpower and the time you put into putting out the deck kind of outweighs the material cost in some ways, So it's more or less like, anyway, everyone I know that's putting in a deck is using synthetic, plastic wood because it's nicer. I think they like it better. So not for like the base of it, not the railings and things. Yeah, like the railings sometimes you want to have, and the railings last longer anyway. Anyway, so polycarbonate I'll put in. If there's something else that's missing, again, this is basically off the top of my head. So yeah, like GE Plastics, who's now Sabic, like makes polycarbonate, right? Like kind of in Indiana. I mean, it's like 6 hours from here or something. But I mean, a lot of UC people work at that plant. But even like grad students have gone there. Anyway, so yeah, this is kind of what I got kind of to look at, right? So anyway, well, I want to go into like electronic waste later. So that's kind of these thermoset plastics, and a lot of these are specialty use in a sense, like polysulfones used a lot for this dishware. The stuff that's not microwave safe, I think, is polysulfone, but it's basically it's used for prison dishes because you can't break it. It's kind of like, seems like a ceramic. And then it's also used like I think it's used for student dishware too, like in the campus probably. But basically it's not really breakable. And when it doesn't make like knife edges when you break it. Anyway, yeah, the acrylic, so some of these I haven't gotten to yet, but anyway, I have the whole, then the additives are gonna be like, there's a ton of additives too. Not sure how, it seems like when you go to the different plastics, then you're gonna have like certain, like for polyurethane, for SBR rubber, like carbon black and silica are like the additives they use mostly, right? And then calcium carbonate's dumped into everything. So there's a company in Cincinnati that's a Swiss calcium carbonate company. What is it? Yeah, Omnia, yeah.
And they work there, they go over like.
Oh, okay. Yeah, we could get someone from there to talk, I guess, but yeah, I have one of my grad students works there. He's in the analytic thing there. But anyway, it's a good company. But in Swiss is always good because they have like so much money. It's like the money place to go. But anyway, Titania is like Evonik and DuPont. So big companies make all these additives too. I mean, they're made in train loads. So, and then they become kind of a problem when you try to recycle things because you don't want to have additives in the material recycling. So separating the additives from the polymer is like a big problem. So kind of knowing what those are is useful. I'm not exactly sure how I'm going to go about talking about additives. So, but mostly I'm just throwing it in with the polymers so far. This thing. So anyway, I thought I'd start with polystyrene on this because it's something that um, That's pretty good. Sorry, I'll turn this thing off. Boy, he's gone. Oh, share the class on Zoom. That's what it's called. You are sharing, screen sharing, stop sharing. It said it's being recorded. Should be being shared too. I think it's automatically shared, right? I just signed into this class. It should be, anyway, I don't know why I said that. It should be okay. Anyway, so this is a polymerization route. So it's a styrene monomer. You take benzene and take ethylene and benzene, mix it together. So ethylene comes from oil. Benzene is one of the cuts in distillation columns. That's just straight oil, distillation products. Ethane comes from oil. Then after cracking, you get ethylene. This is a polyethylene monomer, right? And you use a aluminum chloride catalyst, and you just heat it up to 1,000 degrees C. Seems severe, but it makes styrene. Makes this thing. So it combines the ethylene. Combines the ethylene with benzene. Just they make a bond. It dehydrogenates it. And you heat it up like that. So, right. So you get that, and then you got to free radical polymerize it usually. So you're going to take benzyl peroxide and hide this thing. So benzyl peroxide has this weak ether bond in the middle. So when it heats up, it pops into two of these kind of carboxyl free radicals. And those further degrade, get off CO2, and you get a benzyl radical, two of them. Right, and then those attack this double bond, and then it'll open it up. Gives the free radical in the end. It's protected by the resonance structure of the benzene ring. So the double bonds here can flip over into the single bond. They resonate between. So that's a really stable free radical. So this is like the easiest polymer to make, except this is a carcinogen. You know, so it smells bad. It smells kind of good. Good is a bad thing. Like benzene smells good. It's toxic. Gasoline smell. So anyway, so all right. So anyway, then that free radical goes on to attack another monomer, and then it makes a polymer. Just a chain reaction. So that's a free radical polymerization. That's kind of the standardized free radical polymerization. So because this guy's so resonance stabilized, you can also put an anion here. So you can do an anionic polymerization of this. Right? But the normal polystyrene is made by this free radical polymerization. It's like usually a bulk polymerization. I think you end up with just polystyrene. There's some styrene monomer left in it. So it's dried, and you get the polymer. It's pelletized. So you can do every kind of polymerization. You can do bulk, you can do suspension, so and then you can do colloidal. So with the surfactant. So suspension's advantageous. All right. So the problem with the bulk polymerization is something called the Tromsdorf effect. So as you react it, it's an exothermic reaction. It heats it up, and the increasing heat reverts the reaction. So it kind of kills the polymerization. So bulk polymerization can have this problem that it can kind of destroy itself as it heats up too much. So, all right, so to get around that, you can just dump the monomer into water with something like oil that'll make it form like droplets. When the water cools it down, so you stir it vigorously, and you throw in some catalyst, and then it'll polymerize in the water, like control the temperature of it. So, so there's music. Is that downstairs from here? But we're not above the, we're above air here. It must be out in the football field.
I think it's.
Yeah, it's gotta be. At the other end, the room's down there, you can hear the gym below it, or next door or whatever. Anyway, here we get added music. But anyway, so there's a picture of these kinds of polymerizations in here. Let me see. I should have put it right here. So I'm on 52. Here. This is one of them. This is showing one of the pictures of this. This is showing bulk polymerization. So again, it's like the Tromsdorf effect is the problem here, which causes a reversion of the polymerization, limits the molecular weight you can make. This is a solution polymerization where you're going to put in like an oil so you end up with droplets of the monomer with oil surrounding them, and the catalyst, the free radical agent is put in, then it kind of diffuses over to the droplets that are surrounded by oil, and then basically it ends up making polymer droplets from this kind of big, large size pellets. Or that's suspension. What is this one? Solution is solution where you dissolve the polymer in a solvent. So you wouldn't do that with polystyrene because you have to use something like benzene or something to dissolve it. So it would be a mess, right? But usually you want to do this in water. Like water is the thing that is a good heat transfer agent. It's not toxic. It's got some advantages. You can kind of recycle it in the system. You're not going to have fumes coming off this, right? So it's kind of nicer to use water. And there's monomer droplets with initiator, and there's some kind of something that makes the droplets stabilize, right? So it's basically like another polymer. Then emulsion is a little bit more fancy. So you have, again, like it's just like suspension polymerization, where you have droplets in the water, but the surfactant that you put in soap, it's going to make these little micelles that are kind of less like maybe 100 nanometer diameter, really small. So you have big droplets that are like 100 micron or larger. Then you have like 100 nanometers, so 1,000 times smaller micelles. And the monomer diffuses from the oil droplets through the water to these little micelles. And as it's depleted, as the polymerization goes along, so the catalyst is also in the water, it also diffuses in the micelles. Anyway, there's whole equations to talk about this kind of emulsion polymerization. So they call it emulsion, but it's really a colloidal polymerization because you have these are colloidal droplets. And emulsion is something more like this oil thing where you put oil in and you stir it up. So there's a difference between emulsion and micelle, but it was misnamed emulsion when they first did it, and they just call it that. It's really a colloidal polymerization. So polystyrene you can make all these different ways. If you do it this way, you end up with little beads below a micron in size, right? And those can be used to make exfoliant skincare products. So you can like you can mix that with the oil, and make something you rub on your skin that rips your skin off and makes it like you want to have new skin, get rid of the old skin with that. Anyway, that's a problem with microplastics. Yeah, that's a pretty common product. It's basically those when they get washed off, you go into the water, then you have like these micron size polymer things all over the world. Polar bears eat it or something. So basically, yeah, emulsion polymerization. If you directly use those, you can also just collect the particles and then make them into beads, like millimeter sized beads. And then you make pellets from a bead and extrude. So you can make normal. You can also use this to make like monodisperse polystyrene beads that you can use as like the analytic thing. Like if you want to have a standardized, in other words, you know exactly what the size, they're all exactly the same size. So if you want to use it on a microscope to size scale your images or something, you can sprinkle some of that in, you can see, or to use in a light scattering to see what the sizes you're picking up are. So a lot of like analytic standards are made that way. All right, so yeah, so those are 3 ways to make polystyrene and also to make, oh, I guess I'm saying colloidal polystyrene. Yeah, that is here. So basically, there's a picture, there's a monomer droplet. The monomer diffuses to these so this is an order of magnitude difference in size. Initiator is floating around, also goes there, and then it polymerizes. And again, like these are some of those beads you can make a colloidal crystal with them. Like this is a hexagonal, like a FCC crystal, right, of those beads, because they're all exactly the same size. All right, so that's kind of in the wrong place. But anyway, so the free radical polymerization of this stuff is going to give, this is a like a GPC curve of this. So basically, There's a picture of the GPC in here too. The order of this isn't great. Let me find the GPC picture here. Nope, close. Here, yes. All right, so this is a GPC. So basically, it's going to be an isolated chamber, and you have two spots here. One's empty, one has polystyrene in it. Right, I'm showing it for PET because PET crystallizes. So if it's polystyrene, it doesn't have this crystallization and this melting peaks, but it's got just this glass transition thing here. Right, so basically, when it's cold, it's glass. When you heat it up, it turns into a liquid. And that's it. That's the whole show for polystyrene. So it's not very exciting on a GPC, on a DSC. So it's differential scanning calorimetry. So it's a differential between an empty pan and the other pan and how much heat it takes to reach this temperature. So when you get to the melting point, when you get to the crystallization point, it releases heat. So you get a dip, and when it crystallizes, it consumes heat, so you get a peak. All right, so basically, dips and peaks mean you're going through a melting crystallization. This kind of squiggly thing means you go through a glass transition. So basically, polystyrene is just going to have one glass transition temperature. It's going to be about 110 centigrade, 105, something like that. So anyway, so back to 50. All right. Oh, that's a GPC. Sorry, that's a DSC. I want a GPC. GPC, I had in here somewhere too. Sorry about that. That was a wrong machine. This is GPC. All right. GPC is a column. You have a column that's actually made of a polystyrene gel. So you take polystyrene and you cross-link it with divinyl benzene. So you have like polystyrene is a benzene ring with a vinyl group on it, unsaturated carbons. And if you put another vinyl group on the other side, you have divinyl benzene, which if you put it in with polystyrene, it'll polymerize just like polystyrene, but it's got an extra vinyl group sticking off, so it can make a network. So mix it into like a cross-linked polystyrene. Just mix it in with the other stuff, with the monomer. Then if you take that and you swell it in like toluene, right, it'll make a gel. So you have like a solid gel that's cross-linked. If you put that into a tube that's about like a couple millimeters diameter and maybe 10 centimeters long, and you put it high pressure, a solution of polystyrene, dilute solution of polystyrene in toluene, you push it through that thing. Well, the gel is going to be almost like a plug. It won't move at all. So you crank up the pressure to like 50 megapascal, like 500 atmosphere. So it's called high pressure liquid chromatography. And at that point, it's going to go through, you know. So the gel acts as a selection. So the big polymers, so the gel is like a fractal network, like a forest, right? If you have a small molecule going through that, well, it's going through really slowly because it's a plug. It's like a plug of gel. So it's going through so slowly, the small molecules are like diffusing laterally and going forward. So slowly going forward and thermally like wiggling around. So small ones wiggle all the way through the forest on every branch and every little leaf of the thing. So it takes them a long time because they're exploring the whole thing as they go through. Whereas the big ones, they can't fit into the branches. So they just follow the main path of the thing and come out first. So you get the big things out first and small things come out later. That's what a gel permeation chromatography is. So if you look at this, if you look at what comes out of this anionic polymerized polystyrene, it's got a fairly broad peak to that GPC curve, which is on 50 something here. So this is a fairly broad peak. So that's basically, this is the time coming out of the column. Is at the bottom, it's called the elution time. This is a detector that's measuring like index of refraction, right? And the polymer has a different index than the toluene. So it shows a peak when the polymer goes through. So it's showing the distribution of the molecular weights that you got from it. So from this, you can get the mean value, right? Like the second moment. you can get the higher order moments because you have the whole distribution curve. So you end up with the weight average, which is a ratio of the third to the second moment. And the number average is a ratio, which is the mean. It's the second moment, second divided by the first. So in other words, the average of the molecular weight squared divided by the average molecular weight. This is the cube of the molecular weight divided by the square of the molecular weight. Both of those average. So it's called the weight average because the cube is the weight times the squared one, and the 7 ends up being the mass average. This is the number average, it's just the squared one. So anyway, the ratio of the weight average to the number average gives you the polydispersity, which if this is a spike, all these moments are the same, and this is just one. And if it's broad, then the higher order moments, like the third is larger than the second. So this thing becomes a larger number. So typically, like in this case, it's 2.27 from anionic, from a free radical polymerization. So it's a broad distribution of molecular weights. So I mean, at this end, it's going to be at the high end, it's going to be 1 million, and at the low end, it's going to be 10,000. So there's orders of magnitude difference in molecular weights. It isn't just one chain that's coming out, and that's going to be the Scotch tape container. Like that's the cheapest way to make it, cheapest and easiest. It runs itself. You just throw it in, it makes it. You extrude the container, it's gone. That's it. You know, you're happy. So if you want to get something better than that, you can do anionic. So this thing you can do, like it's not going to be contaminated very easily, that kind of polymerization. Like you can pretty much run it like in a pretty dirty place. It's not really sensitive to the conditions that it's polymerizing under. But if you want to do, so anionic polymerization is the other option. There you're going to use butyl lithium. Okay, so this is like highly toxic material. It reacts with air, it makes like nasty things. This is the case where the guy at Berkeley chemistry lab, they were doing butyl lithium anionic polymerization, and a grad student was doing it at night and then died from exposure to this stuff, right? And then he got sued. He ended up in jail, right? He was a professor. So I don't do this polymerization. Nobody does. It's like, anyway, so basically this is like the lesson learned that you had to have safety, and this is about 10 years ago, I think, right? So anyway, so butyl lithium is a bad thing. And then you have to run it in like ultra dry conditions, right? So all right. So the thing about this is that when you're doing it in a lab and you have a little test tube and you're doing it in, so there's a lot of surface area. Surface to volume is huge, right? And the surface is where all the contamination comes from, like oxygen and oil and whatever. So you have to bake all your glassware, be like super clean. So this is anionic polymerization, but I did cationic polymerization in a lab like that. It's kind of similar. Cationic is actually worse than anionic. It's how you make butyl rubber, right? So, but anyway, I did it in a lab, and yeah, we made some stuff. It was pretty good. And then I went to a factory because they need a lot more to do mechanical testing. So I went to Sarnia, Canada, which is like kind of weird. Like I had to drive across the border with all this chemical making equipment in my trunk. The border guys were pretty excited anyway. But anyway, I got there, and what they had was like in a warehouse is a thing that's like a big reactor, you know, and like so they're feeding in the monomers and the catalyst, and it's to cool it with liquid nitrogen. You have to run these things cooled with liquid nitrogen. They literally just pump liquid nitrogen into the room, like just poured it out of pipes onto the reactor, right? But it turns out like in those big conditions, the surface to volume is like 0. Because you have a thing that's got like 1,000 gallons in it. So it's like there's no surface to volume, it's all just the stuff you put in, and that's all pure. It's basically that thing ran like a charm, like you can make a ton of it. So the larger scale you do, the easier it is to do this kind of polymerization. So you'd think that like this would never be industrially applicable. But it turns out that this polymerization started out as like a little pipe dream somewhere in a lab, you know, ends up being, that's how we make all tires. Like styrene butadiene rubber is made by this process, right? And they do it tons of, you know, I don't know how much, but huge amounts of this material is piped out, right? So all the block copolymers, which I'll show you, they're basically like one chunk of styrene, one chunk of butadiene, right? So you polymerize styrene, then stop and swap the monomers, because these reactions don't have a termination step. So they just will continue forever. And whatever monomer you put in, it'll just add on that monomer. So if you run in polystyrene and then you run out, and they all initiate at the same time, so they're all monodispersed. So this GPC curve is just a spike. And the polydispersity is 1.02 or something, 1.01, right? Even in an industrial reaction. It's even better in an industrial, right? So anyway, all right, that said, this polydispersity isn't necessarily a bad thing, so, all right, so if you want to have, say, mechanical properties, so you pull on it, so you want to have ultimate strength, which is going to be the long chains. It's like you fully pull everything out, and it's just the long chains holding it together. When you initially pull it, it's like the short chains. It's like depending on how you deform it, if you have polydispersity, you get different kinds of, like everyone on a football team does not look the same. Some of them are skinny and can run fast, and some are big and can just kill things, right? So basically the same thing with polymers. You want to have some like short and stout ones, and you want to have some like tall ones, right? Because the thing is going to be put into, it's going to be not on monodispersed mechanical stress is going to go under. It's going to be all kinds of polydispersity, so it has to react that way. So polydispersity is good. If you want to make a block copolymer, sometimes it's better to have more monodisperse. And you can tune it with this too, like you can change it. So there's a lot of control when you have these anionic polymerizations. Anyway, so it's similar. You start with the monomer. I'll show a double bond here, but basically this is going to attack, then make an anion out of the end, and the anion is going to go and attack another monomer. This is for ethylene. But so basically you can do this with polystyrene, polybutadiene. And that's just going to continue electron popping, make anions, and anions will propagate the thing. And again, it doesn't have a termination, so we just keep going forever. The free radicals can terminate with like water, or you can have two of these free radicals can couple together, so you get double the chain molecular weight. That adds to this polydispersity issue. It can backbite, it can go back here and take off this hydrogen, so you get kind of a looping thing going on. And it can also react with water, oxygen, and things. So free radicals have a termination step. That's why you end up with this, or he shows this is two of these recombined with each other that terminates it. That's one of the termination steps. There's a lot of, so there's always an initiation step, propagation step, termination step. And so, and this one doesn't have a termination step, it just has initiation, let's say initiation, and then propagation is attacking one monomers. And it just keeps going forever. Right. So as long as it's clean, like you don't have oxygen. So anyway, so yeah, so anionic, once you get anionic they call it living polymerization, living polystyrene, because it won't stop. Like once you run out of monomer, if you add more monomer, it will continue on. So here they made polystyrene, then they add butadiene, which is this guy. So the butadiene's got two double bonds. So it's butane and it's got two double diene, means like two double bonds in it. One of them will pop off here to the anion, and the other one will pop here into the middle. So you end up with an unsaturated chain, right? So that unsaturated, if you put sulfur in, that'll cross-link. So you want to have, if you want to cross-link rubber, you're going to have unsaturated bonds, and the sulfur will just break that double bond. Well, it can bond with that and another one. So sulfur will make a bridge, and sulfur can bond with itself and make a chain too. So vulcanization of it. So you just put the sulfur in, mix it up, heat it up, and react with those, make cross links. However much sulfur you put in, that's the more sulfur you put in, the shorter the chains between the cross links that you get in a rubber. Right. So this is SBR. It could be a tri-block too. So you polymerize styrene, then you polymerize butadiene, then that runs out of butadiene, then you put styrene in again. So you get SBS, like tri-block copolymer. You can make as many block number as you want. Like you can tune it to whatever you want. So like the Goodyear Aqua Tread, the specialty wasn't the tread, the specialty of it was the way they made the block copolymer, like by tuning the polydispersity, the kind of composition of these things. So that was kind of a trade secret at Goodyear for a while, right? So it's like basically this is a big thing that all these companies have, like chemists that are messing around with this stuff to make a better material, right? So anyway, so that's block copolymers, SBR, anionic polymerization, free radical polymerization, and then so say you want to make like a styrofoam cup out of polystyrene. All right, so the foams are like a big problem for the recycle stream because for one thing, if you crush them, they're going to blow everywhere. Like there's no way to control it. Right? There's an easy way to control it. You just put it in with a little bit of toluene and it makes napalm. Like that's simple. Like you can just take all that foam and just reduce it down to nothing. Like I'm not sure they haven't really done that. I don't know why, but basically that could be done. Like so right now, none of the foam is ever recycled by anybody. Nobody wants to see it anywhere near their plant because it's electrostatic, it just flies everywhere. It'll contaminate everything, right? So don't put styrofoam into the recycle bin. Like I think it'll never really be recycled, except I think that the Cincinnati recycle and reuse place takes it. Do they? Okay. You know that? All right. Do you work there? Or? Oh, really? All right, good. That's good. Yeah, I was wondering if people would want to do that because it seems like a place. It would be fun to go up there, I guess. But so what do they do with it?
Sorted it one day.
Okay, anyway, it's a mess. Like it's a total mess. Because all right, even if you take like you fill this room with styrofoam and then I put a little bit of toluene in, it would make like maybe 1 liter. And not even, It's like there's no material in it. It's like there's no value in it after it's made except to use it as styrofoam, I guess. But anyway, so all you have to do to make styrofoam is like heat it up because there's still some residual styrene monomer in it, or you can kind of soak it in hexane or some other solvent like that. So you just put in a very small amount because there's a big change between liquid and vapor. Right? There's a huge volume change. It's basically a little bit goes a long way. And then so you're going to have some kind of let's see, what is this one? Terminating the bifunctional side. Well, this is just when you want to terminate the anionic, you can put this silane in to kill the reaction. This is the termination step. That's just showing what it kind of in broad terms, like what this would be anionic polymerization. This would be free radical. That's anionic monodisperse. This is block copolymer anionic. All right, so yeah, the styrofoam thing. So basically, no, this is HIPS. Colloidal PS. Styrofoam is here somewhere. Maybe I'll do styrofoam after. Let's do this in the sequence. All right, so ABS is a Lego bricks thing. So that's made. So this isn't really recyclable, So this is made by make copolymers of styrene acrylonitrile. So you have styrene and then acrylonitrile is this monomer, right? So basically, the C double bond N sticks off, and this vinyl polymerizes. So you're going to get this nitrile side group on it, right? Which makes it more tough, I guess, somehow, because I think this hydrogen bonds or something with other groups, or somehow interacts with other groups. And then they blend it with butadiene, so that's the same thing from SBR, which the double bond makes an unsaturated chain, polymerized with acrylonitrile, and you mix this stuff all together. So there's no possibility of recycling this. I mean, you could burn it. You could pyrolyze it to make oil or something. So anyway, that's ABS. So you can see this, it's a fairly complex process. And then you end up with Lego bricks. Right. So anyway. So this is a picture of the ABS wheel that's in the book, that Plastic and Circular Economy book. They're just showing like styrene acrylonitriles, one polymer, SBR rubber, styrene butadiene. So somehow you can make everything in the world from these combination of these things, but SBR is not recyclable. I mean, these things can be ground. Nitrile butadiene, that's a rubber. Not sure what that is. And pure styrene is not, so nothing here is really recyclable in the classic sense of re-pelletizing it or something, right? So maybe this wheel is the wheel of death or whatever polymer stuff, but anyway, then so this is another case similar to the ABS, but predates it. So ABS is 1980s, I think, 70s, 80s, and this HIPS is kind of 1950s, 60s, I think. So this is where this popularized a term called phase inversion. So you polarize styrene and butadiene together by free radicals. So it's like the cheap way to make things, or the easy way to make things. And then you put in the right and you stir it. So it depends a lot on how rapidly you stir it and vigorously stirring it. And the stirring process, like if you stir it too little, it doesn't work. If you stir it too fast, it doesn't work. But during the polymerization, it goes from a butadiene matrix with styrene monomer to a styrene matrix with a butadiene monomer. And with all that mixing, the butadiene domains have little styrene particles in them. So they're rubber domains with little glass reinforcement in it, and the rubber makes the styrene craze a lot. So it's basically, it's going to be kind of a white, like you've seen these plastic, I don't think that's really a Dixie cup, but it's basically a plastic mouthwash cup thing, and it's white. It's polystyrene with butadiene in it, mixed in this way, high impact polystyrene. So not really recyclable, because like, what are you going to do? It's two components. They're not really separate polymers. I mean, they're separate polymers. They aren't really one polymer, right? So it's a mixture of things. The nice thing is it doesn't crack when you bend it. Like it's flexible. So the reason it doesn't crack, when you have polystyrene, so let's see here. So when you have polystyrene, like this is a large piece of polystyrene, you can see these little cracks in it. So it cracks. Those are called crazes. So there's no volume change in it, but what it is like they're little micron size, so smaller than a human hair size, cracks that are bridged by polystyrene fibers. So it makes like a hairy thing. So the fibers kind of reinforce it, but eventually the fibers in the middle break, then a larger crack grows, because terrific criterion is that the smaller the crack tip size, the more stress you have, so it breaks faster. So basically these are micron sized crack tips all throughout the material, so it just crushes down to nothing. Right, so crazes are bad. This is called shear banding. So if you pulled it up 45 degrees, you get these bands, and these are like slip planes across the material. So that's the high regions of the highest shear stress in the material. So the material fails like that, and that happens when you start to put like rubber in with the polystyrene or ABS or something. It's like a Lego brick would fail by shear banding. Polystyrene does this cracking thing. Right, so people have studied this, mechanics, and using the optical microscope to see these things. Anyway, whenever you have this kind of mechanism, so you pull on it, so this is the stress versus the strains, this is the force divided by the area, this is the change in length divided by the initial length. So basically polystyrene looks like that and it breaks. And just straight up bang, that's it, like glass. Then if you start having shear banding, so you add the rubber, so adding butadiene to make HIPS increases the shear banding. So you get a yield point. So it starts to shear band. When it's shear banding, the force actually drops, then it plateaus out. So all along this way, it's not shear banding, it's crazing. So all along this way, it's crazing, and finally it reaches too big of a size. So if you have a lot of crazes, they're smaller, so they don't break. If you have one craze, it gets large and breaks. That's the idea. So the idea is like dump the rubber in to make a lot of defects in it that craze a lot, and then it absorbs a lot more damage before it fails, which turned out to be true. I think that was I think they made the material and they figured that out. It wasn't like they said, oh yeah, we could do this, let's try it. It was more like, let's see what we pour in the pot, what comes out, let's make a Dixie cup. Oh, it doesn't break, I don't know why. And they kind of sorted out why. So this thing's a lot more, the shear banding's a lot easier to understand. You make the material softer and it shear bands, like it's more ductile. So it does that. If it's brittle, it won't do that. So the curve will look exactly the same though. You get like a peak it'll start to shear band, and then all along while you're pulling it out of shear banding, it hasn't failed, and finally it reaches too many shear bands, they lock with each other and it fails. That's like deforming a metal and getting slip planes in it. Kind of the same thing happens. And then if you get it too soft, it'll just be a rubber and it just deforms like that. It doesn't have a yield point and it stretches out. So those are like the three kinds of mechanical behavior of plastics. And they're basically tuned in polystyrene. Anyway, so we're in time anyway. It's not 4:30. It is 4:30. Yeah. All right. So that ABS hips, colloidal PS, then the three polymerization routes. Then this is like so the sketch tape container, which I don't have a picture of here, basically is going to be made on a machine like this. It's an injection molding machine. This is a particularly like dirty one. I went to a place where they made so the speed of these is sometimes fairly fast. Like it'll be going ka-chunk, 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 ka-chunk. So maybe like 20 things a minute that it's making. But there used to be a plant out in like the east side somewhere, where they were making lenses for satellites, for optical cameras, for like spy satellites or something. So they would make like, it would take them like 10 minutes to make one part because they didn't want to have like flow lines and they were PMMA they were injecting. They didn't want to have flow lines that would make it like birefringent. So light wouldn't go through right away. Basically, the process would be so slow, it would spit out one of them. And they had a whole factory. I think it was like Corning or someone that was doing this. Basically, they had a whole factory with maybe like 80 or 90 of these machines doing that like all day. So basically, these injection molding places are kind of interesting to see, I guess. So they'll have these. This is a hopper, but basically there'll be they call it a Gaylor, which would be like a big box of plastic. And then there's a vacuum system that pulls these pellets up, and then the pellets run over to feed into this hopper. So it'll be like a bunch of these Gaylors with kind of elephant nozzles in it that are pulling a section, pulling the pellets up, going, and then on the ceiling you'll see all like that kind of heating tubing, whatever, air conditioning tubing going with the pellets flying through, and it comes down into this hopper and feeds into it. Then that guy is going to feed into this. There's an extruder here that fills up with the pellet as it turns. So it's a reciprocating screw. It fills up, it pulls it back. And once it reaches a point that's happy, it punches into this, and injects the plastic into this mold. So that's the mold, whatever it's making here. So this thing costs like $200,000. So the molds, they're not, basically they think that they're going to make like thousands of plastic parts, maybe millions from this one mold, because it costs a lot of money. The rest of the machine's like junk, but that mold is expensive. Right, so there's certain shops that make these molds. There's a whole industry of just making the molds for injection molding. Like there's a whole business to do that. And then there's industry in like running these kind of injection molding shops. There's an industry in making the pellets. So there's a bunch of different kind of value line of the plastics business, that's going on. That's kind of tied together. This is a video of this. I think it just rejected me. Did something like no. This is the same thing. I'm gonna do that. Oh, it's not even telling me what it was. Slide on. Oh, there. That's good. This is 5 minutes in. It's kind of. I got a few videos that seem like they were local. Let me change my mind. Let's see what this does.
Injection molding is the most common method for mass manufacturing plastic products. Examples include chairs, toys, cases for consumer electronics, disposable cutlery, and my favorite, Lego bricks. Injection molding was invented to solve a problem for billiards.
Oh, it's
In the 19th century, billiard balls were
Right, we're gonna
composed
skip ahead. Da-da-da-da. Da-da-da-da. All right, here.
the clamp. Plastic pellets in the hopper feed into the barrel of the injection unit. Inside the barrel, a screw transports the pellets forward. Heater bands wrapped around the barrel warm up the plastic pellets. As the pellets are moved forward by the screw, they gradually melt and are entirely molten by the time they reach the front of the barrel. Once enough molten plastic is in front of the screw, it rams forward like the plunger of a syringe. In a matter of seconds, the screw injects the molten plastic into the empty part of the mold called the cavity image. The plastic solidifies in under a minute. The mold opens and the part is ejected. The mold then closes and the process repeats. All injection molded objects start with these plastic pellets, which are a few millimeters in diameter. They can be mixed with small amounts of pigment called colorant, or with up to 15% recycled material, then fed into the injection molding machine. Before the mid-20th century, injection molding machines used only external heating of the barrel to melt the plastic before a plunger injected the molten material.
Much detail.
Has flights that wrap around the shaft. As the screw rotates, the flights transport the raw material forward through the barrel. The flights also serve to mix the plastic. The screw action agitates the melting pellets within the flights to create a uniform mixture. And third, the screw action itself heats the plastic throughout. The shaft's diameter increases along the screw so that the distance between the wall and the shaft decreases. The flights then squeeze out air as they move the plastic forward, and they shear the pellets and press them against the barrel's wall. This shearing creates friction and so heats the plastic throughout. This screw-induced shear supplies a majority of the heat needed to melt the plastic, between 60 and 90%, with the rest from the heater bands. The molten plastic flows past the front of the screw through indentations or flutes. When there's enough plastic to fill the mold at the front of the screw, it rams forward like a plunger, injecting the plastic into the mold. The plastic cannot flow backwards because when the screw pushes forward, a check ring is shoved against a thrust ring to block the backwards movement of the molten plastic. This forces the plastic into the mold. Initially, the cavity image is filled with air. As the molten plastic is injected, it forces air out of the mold, which escapes through vents. These vents are channels ground into the landing surface of the mold. They're very shallow, between 5 and 40 microns deep. The plastic, which has the consistency of warm honey, is too viscous to flow through the narrow vents. To speed the plastic solidification, coolant, typically water, flows through channels inside the mold just beneath the surface of the interior. After the injected part solidifies, the mold opens. As the mold opens, the volume increases without introducing air, which creates tremendous suction that holds the mold.
Maybe this is too much detail. Anyway, all right, so he shows, this is fun.
Dented slightly. So if you look closely, you will see circular ejector pin witness marks on molded products. For example, this chair on its bottom has an array of witness marks. When the part drops from the mold, an operator has to remove the sprue, that section of plastic that connected the injection unit to the mold.
So you'll see in the
Screws are manually twisted or cut off the part. Sprues are attached to objects only in molds that make a single part at a time, like a chair. Smaller objects are made in multiples in a single mold. In these, the sprue connects not to the part itself, but to a network of distribution tunnels called runners. The runners fan out from the sprue and connect to each cavity in the mold via a small, typically rectangular entrance called the gate. You can see the gate on plastic cutlery. The parts for model planes typically come still attached to their runners. Molds always have at least two parts, and where the parts of the mold meet is called the parting line. Here on this piece of cutlery, you see the parting line along the side of the fork. When mold halves close, they are never perfectly aligned, nor do they have sharp corners. This creates a noticeable parting line on the molded object. Another very important aspect of mold design is the draft angle. If a part has walls that are exactly 90 degrees, it will be very difficult to eject because its inner walls will scrape the core half of the mold. Also, the vacuum will be difficult to break because air cannot readily enter. However, if the walls are slightly tapered, even just 1 or 2 degrees, it becomes much easier for the part to be removed because once the part moves slightly, the walls are no longer in contact with the core half and air can rush in. One impressive example of injection molding is the Lego brick. You can see the injection point in the middle of a stud, but this is not from a gate or a sprue. The Lego molds use hot runners. Hot runners are a heated distribution network. This keeps plastic inside the runners molten while the plastic in the mold solidifies. This leaves no gates or sprues to be removed.
Go out to
The
line
molded
down.
bricks are ejected, ready to
Your
use.
Same stuff.
The downside is that this setup is more expensive than a traditional cold
They have
runner
a
system.
bunch of injection molding.
On the bottom edge of the brick, you can see ejector pin witness marks. And what's most clever to me is where Lego designs their draft angle. The outside of a Lego brick must be square. So if you cut a Lego brick in half, you can see that these inner supports are thicker at the
Spent a lot of
top than at
time
the
with
bottom.
Lego bricks.
There's a draft angle of about 1.5 degrees.
Yeah,
This helps the ejector pins push the brick off the mold.
There's-
The core
To
half
me, it's kind of
and the
interesting.
cavity half of Lego molds are designed so that the parting line is at the bottom edge of the brick. This hides the parting line. Look around you and see how many injection molded objects you can find. Likely the device you're watching this on has injected molded parts. You should be able to find ejector pins.
That's probably good. But yeah, we could probably quit now, I think, right? So I wanted this, I thought that was worth seeing. Anyway, so yeah. Let me quit there. So let's see, I mostly went through some of polystyrene. I think we're done with polystyrene. I'm gonna try to do that to a lesser degree with the other plastics this week, like on Thursday. So hopefully we can get through that entire 21 list. And then next week do whatever the next thing is to lined up. But anyway, so why don't we quit there for now? Oh, and then that meeting's tonight at 5. So you guys want to, I don't know, might be good to go in a minute. Right, so.